Hello students, this is Jayarpai speaking. In our previous class, we started module 5 concepts, that is instrumental methods of analysis. In our last class, we had just a general discussion on the topic. There we studied how exactly an analytical instrument works, what are the various components of analytical instrument, what are the advantages and limitations of instrumental methods of analysis. Nothing we discussed in a particular. Moving on from there, it is the first instrumental method of analysis as per the syllabus. This is all about colorimetry here. Moving on. Let us first study the principle of colorimetry. Now, when a beam of monochromatic light of intensity I0, when a beam of monochromatic light of intensity I0 is incident on a transparent medium, when a beam of monochromatic light of intensity I0 is incident on a transparent medium, a part of the light having intensity IA is absorbed. A part of the light is absorbed. So absorbed light intensity is indicated as IA. A part of the light is reflected. The intensity of the light reflected is indicated as IR. And the remaining part of the light is transmitted. So transmitted light intensity is given by IT. So total intensity, that is I0, it is equal to IA plus IR plus IT. So IA is the intensity of the light absorbed by the medium. IR is the intensity of the light reflected by the medium. And IT is the intensity of the light transmitted. If you are taking the transparent absorbing medium in a glass air interface, suppose we are taking the transparent absorbing medium in a glass air interface, then IR is negligible. That is, amount of light that is reflected is negligible, and therefore the total intensity of the light is the sum of intensity of the light absorbed and intensity of the light transmitted. Now, ratio of intensity of the light transmitted to that of the original intensity, that is called transmittance. So IT is the intensity of the light transmitted, I0 is the intensity of the incident light. So this ratio is called transmittance. Logarithm of the reciprocal of transmittance is called absorbance. So logarithm of the reciprocal of transmittance, that is called absorbance, that is log of I0 by IT is equal to A. A is called absorbance, and another word for the same is optical density. Moving on. Now let us see what is Lambert's law. So colorimetry is best explained, that is using two laws, that is Lambert's law and Beer's law. Now Lambert's law states that when a beam of monochromatic light is passed through an absorbing medium, the rate of decrease of the intensity of the light with the thickness of the medium is directly proportional to the intensity of the light. I repeat the original statement given by Lambert. When a beam of monochromatic light is passed through an absorbing medium, the rate of decrease of the intensity of the light with the thickness of the medium is directly proportional to the intensity of the light. So this can be understood by taking this this diagram. This is the absorbing medium. We are taking it in a glass air interface. So this is the absorbing medium. This is a solution, okay, and this has the ability to absorb light. We are sending a monochromatic light of intensity I or I0, and some amount of the light is absorbed by the solution and remaining light comes out. And the remaining light that is coming out is a transmitted light. Transmitted light intensity always I mean it is less than that of the incident light because some amount of the light is absorbed here. So intensity of the transmitted light always decreases. Intensity of the transmitted light decreases. That is because a portion or a fraction of the light is absorbed by the absorbing medium. The rate of decrease of the intensity of the light, at what rate intensity of the light decreases with the thickness of the medium. This is the thickness of the medium. This is path length. It is the path travelled by the light in the medium. With respect to the thickness of the medium is directly proportional to the intensity of the light. The rate of decrease of the intensity of the light with the thickness of the medium is directly proportional to intensity of the light. Mathematically, minus di by dt is proportional to I. That is decrease in the intensity of the light with the thickness of the medium. Decrease is shown by negative. Intensity of the light is taken as I. T is thickness is proportional to the intensity of the light, and minus di by dt is equal to k into I, where k is the proportionality constant, and rearranging the terms we get minus di divided by I is equal to k into dt. So if we integrate this, minus di by I is nothing but ln I. So minus di by I is nothing but ln I, and k is a constant. Integration of dt is t. So plus c. So minus ln I is equal to kt plus c. When you are integrating, that is with respect to the upper and lower limits. If you are taking I is equal to I naught, that I naught is the intensity of the incident light, that is before passing through the solution. And then before passing through the solution means thickness is equal to 0. And I is I naught. I naught means the intensity of the light before passing through the absorbing medium. That thickness is 0. And when I is equal to IT, I means IT. IT means intensity of the transmitted light. Transmitted light means the light has passed through the solution and then it has come out. Then it has passed through a thickness of T. Therefore, thickness is equal to T. Earlier thickness is equal to 0. Applying these limits, now minus ln, that is ln, first upper limit, that is IT, ln IT minus ln I naught. Because that is IT is the transmitted light. Transmitted light you are substituting first, minus intensity of the incident light, that is ln I naught, is equal to k constant. Then in the bracket, that is t is there. T upper limit you are applying t only, lower limit is 0. Therefore k into t minus 0. So minus ln, if this one is ln m minus ln n, that is a logarithmic formula is there. Log x minus log y is log x by y. So it is minus ln it by I naught, that is equal to k into t. Or if minus sign taken to the other side, ln it by I naught is equal to minus kt. It by I naught, it is equal to e power minus kt. Ln is nothing but logarithm to the base e. Therefore, it becomes e power minus kt. Then it is equal to I naught into e to the power minus kt. So I repeat, according to Lambert's law, that is mathematical statement, minus di by dt is proportional to I. Minus di by dt is equal to k into I, where k is the proportionality constant. Minus di by I, that is equal to k into dt, that is after rearrangement. When you integrate, minus di by I becomes ln I, k is a constant, dt integration is t plus c. When you are applying the limits, when the intensity of the light, it is before passing through the solution, that is before passing through a thickness T, that means T equal to 0, then the intensity is taken as I naught. After passing through the thickness T, that is T equal to T, the intensity becomes IT. So IT is taken as the upper limit, I naught as the lower limit. So when you apply the limit, minus ln IT minus ln I naught is equal to k into upper limit, that is t, lower limit 0. Now it is minus ln it by I naught is equal to kt. So plus, if you make this side plus, then ln it by I naught is equal to minus kt. IT by I naught is equal to e power minus kt, because ln is nothing but logarithm to the base e. So IT is equal to I naught into e to the power minus kt. Hence Lambert could state his statement could give statement like this, that is, when a beam of monochromatic light is passed through an absorbing medium, the intensity of the transmitted light decreases exponentially when the thickness of the absorbing medium increases arithmetically. What he said is, when a beam of monochromatic light is passed through an absorbing medium, intensity of the transmitted light, that is the light which is coming out, intensity of the transmitted light decreases exponentially. It decreases, it is given by the negative sign, decreases exponentially when the thickness of the absorbing medium, increases arithmetically. As you go on increasing the thickness of the absorbing medium, then the intensity of the transmitted light goes on decreasing. That is what the final conclusion by Lambert's law. There is one more law using colorimetry can be best explained, that is Beer's law. So according to this law, when a beam of monochromatic light is passed through an absorbing medium, the intensity of the transmitted light decreases exponentially when the concentration of the absorbing medium increases arithmetically. So IT is equal to I naught into e power minus kc. If you compare Beer's law with the Lambert's law, it is only change is instead of thickness you have to use the word concentration. Here thickness of the absorbing medium increases arithmetically. Here concentration of the absorbing medium increases arithmetically. As you go on increasing the concentration, then the intensity of the transmitted light goes on decreasing. So Lambert's law and Beer's law, things should be very clear. According to Lambert's law, as you increase the thickness of the absorbing medium, when you increase the thickness of the absorbing medium, intensity of the transmitted light goes on decreasing. If you increase the concentration of the solution and then if the intensity of the transmitted light goes on decreasing, then it is called Beer's law. So Lambert's law and Beer's law, only one word is different, that is thickness in Lambert's law and concentration in Beer's law. Now the combined law, that is Lambert-Beer's law. The relation between absorbance, concentration and path length, it is given by Beer-Lambert's law. Now IT is equal to I naught into e to the power minus kct. So if you combine Lambert's law and Beer's law, it is Lambert's law is IT is equal to I naught into e to the power minus kt, and Beer's law is IT is equal to I naught into e to the power minus kc. Now if you combine, you get IT is equal to I naught into e to the power minus k into c into t. And if you take, if you rearrange, then IT by I naught is equal to e to the power minus k into c into t. If you take the reciprocal, that becomes I naught by IT, that is equal to e power plus kct. If you take logarithm with respect to the base e on either side, then log I naught by IT to the base e, that becomes kct, because log e to the base e is 1. Now change this logarithm from natural logarithms to common logarithms, then you have to multiply by 2.303, then into log to the base 10 I naught by IT, that is equal to kct. Log I naught by IT, that is equal to k divided by 2.303 into ct. This k by 2.303 is taken as a epsilon. Log of I naught by IT is nothing but a, you have already studied. So a equal to epsilon ct, where t is the path length and epsilon is nothing but molar extinction coefficient. Epsilon is nothing but molar extinction coefficient. It is a constant for a given substance at a given wavelength. So molar extinction coefficient is a constant for a given substance at a given wavelength. If T is kept constant, then A is proportional to C. In this expression or in this equation, if T is path length is kept constant, then A is proportional to C, because epsilon is anyhow a constant, that is molar extinction coefficient. Hence a plot of absorbance against concentration should give a straight line. Okay, here this formula A equal to epsilon Ct is very important. You should be knowing the significance of the terms involved. T is path length, C is concentration, epsilon is molar extinction coefficient, which is a constant for a given substance at a given wavelength. A is absorbance. Moving on. Now, let us study something about colorimetric determination of copper. For that, what is the instrumentation required? Now, in colorimetric determination of copper, any colorimetric determination for that matter, we need a white light source. That is source of light or visible source of light, and generally tungsten bulb is used as the light source. And then we need a filter, because light source means you have a mixture of wavelengths, and we need to isolate a particular wavelength, and that particular wavelength of light is made to pass through the absorbing medium. For that we need a filter. Filter is a device for isolating a monochromatic light. So filter is a device for isolating the monochromatic light from the visible light source. Sample, it is taken in a glass cell, and photocell, or it is a detector. It converts emitted light into electrical signal, or transmitted light into electrical signal. So source means it is a tungsten bulb. It is used as a visible light source, and visible light source, it is a mixture of many wavelengths, and if you want to isolate a particular wavelength in order to get a monochromatic light, then we need filter. Filter is a device for isolating monochromatic light from the spectrum of light. Sample, it is taken in a glass cell. Photocell or detector, it converts the transmitted light or emitted light into the electrical signal. So it is schematic picture of colorimetric determination. It is a source of light. It contains a mixture of wavelengths. It is a spectrum for that matter. And filter, it is the one which isolates a particular wavelength from the source of light. That is a monochromatic light. That monochromatic light is made to pass through an absorbing medium, that is taken in a glass cell. This is the sample. And some light, it is incident light, that is I0. So I0 is the incident light, and here some light is getting absorbed, that is A, and then the light comes out, that is transmitted light or emitted light. This transmitted light, it is received by the photocell or detector. So detector now converts this transmitted light into electrical signals. Electrical signals are then amplified, then processed in a signal processor, and finally it is converted into digital form, and here that gets displayed on the display of the instrument. So it is I0 is the incident light, that is monochromatic light. Monochromatic light is passed through an absorbing medium. Some light is getting absorbed, and the amount of light getting absorbed is recorded as absorbance. The remaining light comes out, that is the intensity of the transmitted light, and it is received by the photocell, and photocell actually develops an analytical signal, and then it converts that analytical signal into electrical signal, and electrical signal amplified and processed in a signal processor, and finally it is converted into digital form, and the digital signal gets displayed on the display of the instrument. Now let us see it's a colorful picture of the schematic representation. This is a light source, and here we are getting many wavelengths because it is a mixture of all the wavelengths, and it is a collimator, and a collimator lens. This light is made to pass through, and this monochromator, or that is prism, and when the white light is made to pass through the prism, so it undergoes dispersion. It gets dispersed into different colors, and particular wavelength of light is chosen. For that we have wavelength selector, or that is filter, and a particular wavelength of light is selected, chosen, and it is made to pass through the sample solution taken in the test tube or cuvette, and This is I naught, that is intensity of the incident light, and this is IT, intensity of the transmitted light. In between some light is absorbed, and then it is detector. Detector receives the transmitted light intensity, and it converts it into electrical signal. Electrical signals are amplified, then processed in a signal processor where all the calculations take place, and finally the signal is converted into digital form, and the display, on the display some digits get appeared, and these digits we are taking a note of the, we are taking a note as absorbance, or the amount of light absorbed by the solution. Moving on, now procedure part. In this we are taking first copper sulphate solution, and we are transferring that copper sulphate solution in a burette, and then we are taking 2, 4, 6, 8 and 10 ml of the solution into different 50 ml standard flasks. We have to label 50 ml standard flasks 2, 4, 6, 8 and 10, and as per the label you have to draw out exactly these volumes into different standard flasks. Now you have to collect one test solution from the teacher or examiner, and to the test solution we don't know what is the volume of copper sulphate present, so that is unknown to us, that we have to find out from the experiment. And 5 ml of ammonia solution to be added to each of the standard flasks. To all the standard flasks we have to add 5 ml of ammonia solution, and it is to be shaken well and then diluted up to the mark with ion exchange water and shaken well for uniform concentration. To all the standard flasks we have to add 5 ml of ammonia solution, that is ammonium hydroxide in fact, and the solutions are diluted up to the mark with ion exchange water and shaken well for uniform concentration. Now prepare a blank solution by diluting 5 ml of ammonia solution in a 50 ml volumetric flask with ion exchange water and mix well. Means blank solution is the one which is absolutely free from the test solute. So here we are not taking any copper sulphate solution, we are taking only 5 ml of ammonia, and then we are diluting it up to the mark with ion exchange water in 50 ml volumetric flask. Now after 10 minutes we have to measure the absorbance of all the solutions against the blank at 620 nanometer using a photoelectric colorimeter. So 620 nanometer wavelength light we are choosing, that is because the compound that is formed after mixing copper sulphate and ammonia solution, that is cuprammonium sulphate, this complex absorbs maximum light at this particular wavelength, and therefore we are measuring absorbance of all the solutions against blank at 620 nanometer using a photoelectric colorimeter. And then we have to all the readings are to be calibrated, and a calibration curve is to be plotted taking absorbance along a y-axis and volume of copper sulphate solution along a x-axis. And from the calibration curve we are finding out what is the volume of the copper sulphate solution given in the test solution, that is volume of the test solution, because I told you that how much copper sulphate solution, test solution is given, it is kept secret. It is like we don't reveal it in the beginning. So after doing the experiment we have to find out what is the volume of the test solution, and once you know the volume of the test solution you can calculate the amount of copper in the given solution. So what amount of copper is present in the given test solution, that is copper sulphate solution, that we can do it, that is by simple calculations. So it is the procedure. Now I told you, you have to prepare 2 ml of copper sulphate, you have to take 2 ml copper sulphate, 4 ml copper sulphate up to 10 ml copper sulphate in different 50 ml standard flasks. Now I have shown the first standard flask where you have taken 2 ml copper sulphate and then you have added 5 ml of ammonia to it, and final volume is made up to the marks. You will get light blue colored complex here, that is nothing but cuprammonium sulphate, copper sulphate and then ammonium hydroxide added, then you get cuprammonium sulphate. This ammonium hydroxide is also known as ammonia solution. Cuprammonium sulphate is a dark blue colored complex. Depending upon the concentration of the copper sulphate taken, the intensity of the color varies. So it is 10 ml copper sulphate solution. Here the intensity of the cuprammonium sulphate formed is very high. So in between the solutions I have not shown, that you can make out 2, 4, 6, 8, 10. The intensities of the blue color for other solutions, it will be in between these two. Now the volume of the copper sulphate solution we are taking like this, 2, 4, 6, 8, 10. To all the solutions we are adding equally 5 ml of ammonia solution. Test solution we don't know how much volume of copper sulphate is there, but to that also we are adding 5 ml of ammonia. And then we can calculate weight of copper in the solution, that is 2 into 5 we have to do, 4 into 5, like that you have to calculate. Not like that. Weight of copper in the solution, it is calculated using this formula, that is 2.037 into volume of the solution. Volume of the solution is given over here, just multiplying 2.037 into 2 and to be entered here. Then 2.037 into 4, that value to be entered here. Like this for all the volumes you have to calculate. But test solution volume you don't know how much it is, so you cannot calculate weight of copper here in this table. That you will calculate only after plotting a graph. Now absorbance value, whatever you are getting, that is from the instrument, those values you have to record here. For 2 ml what is the amount of light absorbed, that is entered here, and 4 ml what is the amount, absorbance. So absorbance is is found to increase, that is with the increase in the concentration of the copper sulphate or a volume of copper sulphate solution. As the concentration of the copper ions increases, then the absorbance value also goes on increasing. Now we have to draw a calibration curve by plotting absorbance against volume of copper sulphate solution. So light colored solution, it absorbs less light, and intense dark colored solutions absorb more light, and therefore when you measure the absorbance, first initial value will be low, but as you go on proceeding, then absorbance value goes on increasing, indicating that absorbance is directly proportional to the concentration of the copper ions. Next you have to plot a calibration curve, that is taking absorbance along y-axis and concentration of the copper ions along the x-axis. So you will get a straight line passing through the origin, and after getting a straight line, what is the absorbance of the test solution, that whatever it is recorded here, absorbance of the test solution, that is to be marked on the y-axis, that is absorbance of the test solution. What is that value? Accordingly you have to mark it here. Corresponding to that value you have to draw a dotted line and see where exactly it meets the main line. From there you have to drop a perpendicular, that will give you the concentration of the copper ions in the given solution. So from the absorbance value of the test solution, you can find out what is the volume of the test solution, which you didn't know earlier. You knowing that value, that is volume, how much it is, and to that volume if you multiply by 2.037, then you will get to know how much copper is present in the test solution. So using the calibration curve, first we have to find out the volume of the copper sulphate solution given, that is the volume of the test solution, and finally we are calculating the amount of copper in the given solution, and that we are reporting as a concentration of the copper in the test solution in terms of milligrams. Hope I have made the things very clear to you, and this experiment you have already done in the laboratory. Only theory part you have not studied elaborately, and in this class I have explained theory as well as a procedure elaborately. So after listening to the video, if you feel that certain concepts could have been explained more or needed more clarifications, in that case anytime you can call and get your doubts clarified. Thank you.